Good morning. In today's video, we're going to look at section 6.1, velocity and net change, which really is a review of a lot of the stuff that was done in Calc 1, where we look at position, velocity, displacement, distance, and particularly the relationship between position, velocity, and acceleration. So let's just quickly review a few of those concepts. The first thing, remember, your position function is represented as s of t, where t stands for time, and the position represents an object relative to the origin at a particular time. And then velocity, if you recall from Calc 1, is simply v sub t, and it is the derivative of s sub t. And then we can add to that acceleration, a sub t, if you recall, is simply the derivative of v sub t. Now, displacement represents distance traveled between two time periods. So when we talk about displacement, we will look at displacement of an object between time A and t equaling b, where some value b, of course, is greater than a. So your displacement is simply the position you end up with at B minus the position you started at A. And it doesn't matter where it went in between. So displacement is different from total distance traveled. Remember that. We'll look at that in the next one. This can all be represented by the fact, if you are given the velocity, you can go the velocity from A to B and take the integral of the velocity with respect to time. And we know this because it's representative of this relationship here. Okay? If velocity is the derivative of s sub t, then your position, of course, is going to be the integral of the velocity function. Okay, now total distance traveled, of course, could be much more than your actual displacement. Again, we will go between t equaling a and t equaling b, where, of course, b is greater than a. But in this case, when we look at the integral from a to b, we want the absolute value over those intervals. Total distance traveled is always a positive value. Okay? So in the same respect, when we think about what do I mean by the absolute value of the velocity, the absolute value of the velocity is the speed, because like total distance traveled, speed is also always a positive. At some specific time t. So these relationships are pretty important, and we can solve a lot of different types of problems with them. So for example, I'm going to move my screen up. Let's suppose a jogger runs along a straight road with velocity equal to 2t squared minus 8t plus 6. And we're going to look at time between 0 and 3 hours. So if we were to sketch a quick graph of this function, it is clearly a parabola. It's a positive parabola. If you go ahead and factor it, you will see you can pull out a 2 and factor what's remaining. You get t minus 1, t minus 3. So your zeros are at 1 and 3. If we were to locate the y-intercept, you can clearly see by plugging in 0 for t, your y-intercept's at 6. So our parabola is going to look something like this. I didn't quite make my 3 there, but that's okay. Whoops, I'll do it again. Okay, and we only want to go to 3, so sorry about that. There we go. Now, because this is a velocity function, we are moving in a positive direction when your graph is above the x-axis, and then in a negative direction when your graph is below the x-axis. So keep that in mind, because again, we're looking at velocity. So moving forward, think about that, and then between the first hour and third hour, they are moving backwards. So how would we find displacement of our jogger over the interval 0 to 3? Well, we learned in Calc 1, because displacement, we need to look separately at the positive and negative. There's a couple ways we can do this. We can look at each integral and integrate from 0 to 1 of our velocity function. And I'll let you pause and do some integration real quick, but you can see real quick, I'm not going to do the integration here. You can do the integration on your own, and then you should get 2/3, what are you going to get? You're going to get 2/3, here we'll do this one together, 2/3 t cubed minus 4t squared. Yeah, because you're going to divide by 2, so you get 4 plus 6t. We're going to go from 0 to 1. And when you plug in, the zeros are going to cancel, of course. You get 2/3 minus 4 plus 6. You actually end up with 8/3 when you do the math. So this area is 8/3. We can do the same thing from 1 to 3. And again, you can hit pause and work through it, see what you get, but you actually end up with negative 8/3. So this is negative 8/3 down here. So that kind of tells me if I were to integrate fully from 0 to 3 of my velocity function, and again, to practice your integration, you can try it on your own. Remember, when you integrate, you end up with a net area. Net area is what we want for displacement. So if you were to integrate from 0 to 3, you should get 0, because our displacement ends up being 0. Which means after 3 hours, this jogger returned to the starting point. Now, that's your displacement. Total distance traveled is another matter. Obviously, the jogger traveled a lot and did a lot of jogging in those 3 hours. So when we look at total distance traveled, you would need to take each separately as we did, but use the absolute value. So essentially, you would have to integrate from 0 to 1, absolute value VT, which is positive 8/3, and then from 1 to 3, the absolute value of VT, which is the absolute value of negative 8/3. And the total distance traveled would end up being 16/3. So keep that in mind, the difference between your displacement and your total distance traveled. Displacement is your net area. That is if you fully integrate from 0 to 3. But when you're talking about total distance traveled, we're talking about total area with an integral, and you have to use absolute value. Another point I want to make here is, and you might get a problem like this in math lab, and that is use your understanding of what an integral represents. So let's suppose in math lab we get a problem. I'm going to keep this very simple right now. But we're not working with a curve, we're actually working with straight lines. So let's suppose our velocity function has a constant increase in velocity, 1 to 2, and then remains to 3, and then comes down as a straight line. But let's suppose you are not given the actual function. Now, you can certainly figure it out. You know how to get the equation of a line. It's very clear. You have a starting point at 0, 0. The line goes through the point 1, 2. You can very clearly see what the slope is. Rise over run is 2 over 1, so your slope is 2, and you can come up with your equation of a line. But let's make matters a little bit simpler here. When we're talking about to get our displacement and to get our total distance traveled, remember, we need to look at each section. So let's start here. We would need from 0 to 1 of our velocity function. But what is an integral between 0 and 1? Isn't it simply just the area under the curve? So if you don't want to integrate, you don't want to come up with that equation and go through the integral process, use what you know about area of basic geometric figures. This is a triangle, right? Isn't the area of a triangle simply 1/2 base times height? So 1/2, your base is a unit of 1, height is 2, 1/2, 1 times 2. Looks like that just comes out to 1. 1. Right? Now let's do the next geometric figure I see. Well, that would be between 1 and 3, v sub t dt. Well, we just have a rectangle, base times height. So we have 2 by 2, that's 4. Okay? So in other words, you don't need to overcomplicate. Use what you know about what a defined integral is. It is simply the area under a curve between point A and point B, and so on. So you can go on and you could finish this problem and find total distance. Just keep in mind when you do this one, you are talking about a negative area, all right, where this one would be positive. And then you can find total distance and displacement as well. Now, we can also use what we know about the relationships that were given prior to talk about the future value of a function. And this was also discussed very briefly in Calc 1. But let's suppose you were given a velocity of an object moving along a line with an initial, whoops, sorry about that, position S sub O. Then the future value, or the position for any future time, for any time being greater than or equal to 0, because S sub O represents what your position is at time 0, that future position, well, it would have to be your initial position plus the integral up to that future time you're choosing of your velocity function. Okay, so this is your initial position here, and this represents the displacement from 0 to t. You can also use this same idea to get a velocity function from a given acceleration. So given a sub t of an object moving along a line and an initial velocity of v sub 0, so the initial speed of your function, then you can get the velocity of the object for any future time that is greater than 0 would be given by v sub t equals your initial velocity plus the integral up to that future time of your velocity function. So let's take a look at a quick example. I paused and drew some of it out for you. Suppose we have this block hanging, this block here hanging from a spring, right? Now, normally the block will sit at the 0 line, all right? But we're going to do an initial position of -1/4, and we're going to assume that our position is positive as we move forward, move up. So at initial time, we have pulled the block down. So our initial position, our S sub 0, equals -1/4. We know that the velocity of this particular spring, when we let go of it, will be 1/4 sine t. What we want to find is the actual position function for when t is greater than 0. So let's think about that. S sub t is going to equal the integral of v sub t dt. This is what you learned in Calc 1. We used what we called the antiderivative method. So what does that mean? Well, we simply took the antiderivative, right, which would be 1/4 sine t dt. Do a quick derivative here. That is negative because the derivative of sine is negative cosine. Cosine t plus c plus some constant. If you recall, we found c by using our initial position. By doing this. So this is s sub t, which gives us part of our position function, but we don't know yet c. Again, this is how we worked it out in Calc 1. We said, okay, but I know s sub 0, which would be negative 1/4 cosine 0 plus c, has to equal negative 1/4. Yeah. And I could work that out. I could do some math. Right, so c would be equal, I don't need that extra equal sign. C then would be equal to our negative 1/4. I'm going to move this over to the other side, plus 1/4 cosine 0, which is negative 1/4 plus, well, cosine 0 is just 1/4, and it's 0. I get c equals 0, which then tells me, hey, s sub t is then negative 1/4 cosine t plus 0. Now, not that this method, that was not a difficult method to use. You just had to take a second step to solve an additional equation. But using the theorem we just discussed, let me scroll up, which would be right here, it just kind of allows you to do it all in one step. That's all. So where this is called the antiderivative method, this is simply using essentially what is the fundamental theorem of calculus. So using that other method, again, not that much different. I'll call it our Calc 2 method. Often is also called the fundamental theorem of calculus method. So we could do s sub t. Well, it's going to equal s sub 0 plus the integral from 0 to t vx dx. So I know that is now negative 1/4 plus, you have to integrate, right, from 0